Hey guys, JLand Bio here to talk to you a little bit about the exciting world of kinetic molecular theory. So what we are going to dive into today is on a molecular level, what goes on with different states of matter, such as solids, liquids, and gases. What does that look like on a molecular level? How do those molecules behave, and how does that translate into some of the chemical and physical properties that occur with these chemicals on a bigger or macroscopic scale? So we're going to dive into that here in just a moment. Let's talk about some learning targets for this video. Hopefully you will be able to understand the key concepts behind kinetic molecular theory and how it explains the movement of all particles, and to differentiate on a molecular level between solids, liquids, and gases. We have quite a few vocabulary terms for you to be able to understand. The first being kinetic molecular theory. We'll dive into what is an ideal gas. We'll talk about elastic collisions, diffusion, effusion, real gas, fluid, and surface tension. So before we begin, let's establish some ideas about kinetic molecular theory and just particles on a molecular level in general. Now, when we look on a molecular level, all particles are in constant motion, regardless of whether it is a solid, a liquid, or a gas. Now, different states of matter have different motion of particles. You can probably imagine that gas particles will move the fastest, then liquid, and then the slowest moving particles are solids, where those particles actually don't move a whole lot, they just vibrate in place because they're so compact with one another. Now, when we talk about kinetic molecular theory, we're really going to focus on gases, and primarily that of an ideal gas. Ideal gases are different than real gases because ideal gases do not deal with intermolecular forces. We don't focus on that. So you think about to our last unit, particles have interactions with one another due to intermolecular forces such as London dispersion, dipole-dipole, and hydrogen bonding. Real gases have those. However, ideal gases, we assume that the particles do not have them. Now, some gases behave more like ideal gases than others. Nitrogen, for example, is a very nonpolar molecule, so it will behave more like an ideal gas. Whereas something that is very polar, like water or hydrochloric acid, will not behave like an ideal gas because it has very strong intermolecular forces associated with it. And again, there are 5 key assumptions to kinetic molecular theory. Number 1 being that gases are made up of particles that are very far apart relative to its size. Gases can actually occupy a volume of about 1,000 times greater than that of a solid or liquid. So if we have some ice and we melt it and then we boil it, creating steam, that steam will have a volume of about 1,000 times greater than that of the water or the solid piece of ice that you had. Alright, so those molecules, relatively speaking, are very, very far apart when you compare them to a liquid or a solid, where they're relatively close together. The second assumption is that collisions between gas particles are 100% elastic. So when two particles that are moving through a gas collide with one another, we assume that they're 100% elastic, which means that energy is conserved. Think about like a bouncy ball, right? You throw the bouncy ball on the floor, it bounces up. Most of the energy is conserved in that and not given to the floor because the ball bounces up. Whereas if I take a bowling ball and I throw it on the floor, the bowling ball is not going to bounce very much because most of the energy is not conserved in that. Now, this is not necessarily true in real gases because some energy is always lost in a collision of two objects. You can learn more about that when you take a physics class, but for our intensive purposes, collisions between gas particles are 100% elastic. The energy in those collisions is always, always conserved. 3 is that gas particles are in a constant, rapid, and random movement. So gas particles, because they have high amounts of kinetic energy, are moving faster than those at a solid state or a liquid state. Again, that is due to higher amounts of kinetic energy. And they're continuous, they do not stop moving, they move very quickly, and they have very random movement. Those molecules don't necessarily move in one direction. Okay? And again, this means that they have lots of kinetic energy to make that movement possible. Fourth assumption, and it kind of goes back to what we talked about earlier, is that there's no force of attraction between the gas particles. We assume that the gas particles have no intermolecular forces. Now, this is not true of a real gas either. Intermolecular forces play actually a large role in the behavior of matter. But because some gases are more ideal than others, we can make the assumption that there is no force of attraction between those particles, meaning that how those particles behave is solely based on the kinetic energy that is present in those particles. And lastly, number 5 is that temperature is a measure of average kinetic energy. And this is really important because most people think that temperature is a measure of heat, and that is not the case. Heat is about energy transfer. So temperature is a measure of kinetic energy. Lower temperature means lower kinetic energy. It makes sense. Solid objects, which have a lower temperature, will have lower amounts of kinetic energy. Their molecules will not move as much. Whereas something like a gas that has higher kinetic energy, those particles will be moving faster and therefore have a higher temperature. So I think you get the good idea here. So what are some key properties of gases? And again, these are things that you probably already have an idea about, but we'll elaborate on them anyways. The first is that they have no definite shape or volume, meaning that the gas will take the shape of whatever container you put it in. It's considered a fluid, which seems weird because when we think typically of fluids, we almost always think of liquids. And liquids are fluids, but gases are as well, because fluids have the ability to flow, whereas solids don't necessarily have that ability. Gases have a very low density, meaning that the ratio of mass to volume is very, very low. They have the ability to be compressed. So think about if you have like a gas grill at home, or if you utilize natural gas as a way to heat your home. You've got those big tanks on the outside of your property somewhere. That is compressed gas. You can compress gas, whereas you cannot compress liquids or solids. And gases also have the ability to diffuse, which means mixing of particles due to random motion, and effuse, which means they can move through a small hole. Diffusion is very simple to think about. If somebody farts in class, it really, really stinks for a really, really short period of time. But the molecules diffuse. And as the molecules diffuse, you don't smell those fart particles anymore. Yes, I just said fart particles. No, that is not the word of the video. It would be really embarrassing to make you write the words fart particles on a sheet of paper. I will not do that, so I will make the word of the video diffusion. Okay, the word of the video will be diffusion. Do not write down fart particles. Let's move on. Properties of liquids: no definite shape, but has a definite volume. So it does take the shape of the container it is in, but it has a definite volume. So regardless of whether I have 12 milliliters, or I'm sorry, 12 ounces, no, we'll go. Stay away from the ounces, Joe Lamb. All right, we're not talking about imperial measurements. We're going to go to metric. If I have 350 milliliters in a soda can, or 350 milliliters in a glass, it's still the same volume. It just takes the shape of the container it's in. It's still considered a fluid because it can flow. It has a higher density than gases and still cannot be compressed. It can diffuse or effuse as well. Think about if you've put food coloring inside of water, what has happened there. It also has surface tension, which is a force that decreases the surface area to the smallest possible size. So again, it kind of goes back to taking the shape of the container. But there's also pressure that's there as well. Think about like the little water bugs or leaves that when they fall on the lake, they don't actually break that pressure of the surface tension, so they float almost above the water. They don't float in the water, they actually like skid across the top. That's because they don't break the surface tension. It's pretty cool. And then capillary action, which is the attraction of a liquid to a solid. So if you've ever done something, like there's a little trick you can do with water in a straw where you can actually get the water to go up the straw. That is capillary action. That's also how trees can take water from the roots, which are in the ground, and take it all the way up to 30 meters or so high, is because of things like capillary action. It's pretty cool stuff. Properties of solids. Solids have a definite shape or volume. Definite shape and volume, I'm sorry. Particles vibrate in a fixed position. So the particles still move. They just happen to move in a fixed position. So they just vibrate back and forth. They cannot be compressed. They have a very high density and cannot diffuse or effuse. So long story short, the kinetic molecular theory actually helps us explain solids, liquids, and gases on a molecular level, and they have a variety of different properties. Properties that you'll need to make sure that you know and understand. So that's the video, guys. Hopefully you got a good idea of what's going on here. We'll talk a little bit more about kinetic molecular theory moving forward in our next unit. Hopefully we met the learning targets, and we will see you next time, guys. Have a great day. Bye-bye.